Welcome to Calm and Clever. It's lovely to have you here tonight. Wherever you are right now, whatever corner of the world has gone quiet around you, I'm glad you found your way to this little pocket of calm. Maybe you're tucked under a blanket with the weight of the day finally lifting off your shoulders. Maybe there's a lamp still on somewhere across the room, throwing soft shadows you've stopped really seeing. Maybe you're on a train or a couch or curled on your side in a bed that's slowly warming to the shape of you. It doesn't matter where exactly. What matters is that you're here, and that for the next little while, you don't have to do anything at all except listen and drift and let your mind go soft at the edges. So before we begin, I'd love to know, where in the world are you watching from tonight? What time has it become in your corner of things? Whether it's late evening or the deep hush of the small hours, whether the street lights are still buzzing outside or the whole town has gone dark and still, leave a little note if you feel like it. There's something gentle about imagining all of us scattered across the planet in different cities and different time zones, all settling down to the same quiet voice at once. You're not alone in this, even though it feels private. There are others out there doing exactly what you're doing, somewhere far away, getting sleepy too. And if you enjoy these slow journeys, if you'd like more nights like this one to drift off to, a quiet like and a subscribe really does help this sleepy little channel keep going. I mean that warmly, not as a demand. Small creators like me genuinely rely on it, on those tiny gestures, to keep making these. And to those of you who've already subscribed, who keep coming back night after night, thank you. Truly, you've made this little ritual into something real, and I don't take that lightly. Now here's my promise to you tonight, the same one I always make. We're going to take this slowly, softly. There's absolutely no need to follow every word, no need to grasp every idea, no test at the end of any of this. If you drift off before we're through, that's not a failure, that's exactly the point. The ideas will still be here. The strange dead star we're going to talk about will still be out there in the dark, doing what it's done for 10,000 years, long after you've fallen asleep. So you can let go of any pressure to pay attention. Let the words wash over you. Let some of them land and let the rest just float past like leaves on slow water. I will, as always, try not to make this so interesting that it keeps you awake, though I have to be honest with you. The thing we're talking about tonight is a little bit spectacular, and I may not entirely succeed. But if it does keep you up for a few extra minutes, well, at least you'll have learned something strange and beautiful about the universe before you sleep. That seems like a fair trade to me. So, settle in. Get comfortable. Let your breathing slow down to match the pace of my voice. And let me tell you about the strongest magnet in the entire universe and the fact that it is, of all things, a dead star. Let me start with a single moment in time. A specific date, the 27th of December in the year 2004. Now, on that day, here on Earth, life was going on as it always does. People were finishing the last of the holidays, putting away decorations, going about their ordinary quiet lives. Nobody looked up. Nobody felt a thing. And yet in that moment, something reached across an almost unimaginable gulf of space and touched the very air above our heads. We didn't see it with our eyes. We had no warning. But our instruments saw it, and what they recorded is one of the most astonishing things ever to arrive at our planet from somewhere else. On the far side of our galaxy, roughly 50,000 light-years away, a dead star had done something violent. 50,000 light-years. Let that distance settle on you for a moment slowly, because it's almost too big to hold. A light-year is the distance light travels in a whole year, and light is the fastest thing there is, racing along at a speed that would carry it around the entire Earth more than 7 times in a single second. Now imagine that blistering speed sustained, not for a second, not for a day, but for 50,000 years without pause. That's how far away this thing was. It sits over near the crowded heart of our galaxy, on the other side of the great wheel of stars we live in. From where you're lying, it's about as far as anything in our own galaxy ever gets. And from all the way out there, this dead star flared. In about 1/5 of a second, in less time than it takes you to blink, this object released more energy than our sun gives off in roughly 250,000 years. I want you to really sit with that one, because it's the kind of fact that doesn't quite fit inside a human head, and that's all right. Our sun is not a small thing. It's a furnace so enormous you could fit more than 1,000,000 Earths inside it, and it has been pouring out light and heat steadily for over 4.5 billion years, warming our days, growing our food, holding our whole little planet in its orbit. Everything that has ever lived on Earth has lived on the sun's generosity, and this dead star, in 1/5 of 1 second, gave off more than the sun manages in 250,000 years of patient burning. All of it. All at once. In a flash shorter than a heartbeat. That kind of event has a name. Astronomers call it a giant flare. And the object that produced this one has a name too, a string of letters and numbers that sounds like a code, because in a way it is. It's called SGR 1806-20. We'll come back to what that name actually means a little later, when your mind is even softer than it is now. For tonight, just let it be a label for a particular dead star, sitting 50,000 light years away, that on one December day let out a scream of energy across the entire galaxy. And here's the part that always stops me. That flash didn't just stay out there in the dark. It traveled. For 50,000 years it raced across the emptiness, a pulse of gamma rays and X-rays spreading outward, thinning as it went, until at last, on the night of December the 27th, 2004, it arrived here, at us, at our small blue world tucked away in a quiet arm of the galaxy. And when it got here, it actually did something. It physically disturbed our planet. High above your head, far above the clouds and the weather, far above where airplanes fly, there's a layer of our atmosphere called the ionosphere. It's the thin, electrically charged upper edge of the air, where the gas is so high and so exposed to space that it gets stripped and energized into a faint, glowing shell wrapped around the whole Earth. It's the layer that radio waves bounce off, the layer that lets signals skip around the curve of the planet. It's gentle and high and almost nothing at all, just the faintest breath of air at the very top of the sky. And when the flare from SGR 1806-20 arrived, it reached down and disturbed that layer. The sudden flood of radiation ionized the upper atmosphere on the night side of the Earth, the side turned away from the sun, where you'd expect that layer to be at its calmest and quietest. Scientists later studied the way certain very low-frequency radio signals had changed in that moment, the way they bounced differently off the suddenly disturbed sky, and they could read in those changes the fingerprint of the flare passing through. This is recorded in the work of a researcher named Inan and colleagues, published a few years after. The flare from a dead star on the other side of the galaxy had rearranged the upper air of our planet. I want you to feel how rare and strange that is. There are so few times in all of history when an object outside our own solar system, something not the sun, not the moon, not a passing comet, has had a direct, measurable physical effect on the Earth itself. Stars are far, space is enormous and mostly empty, and almost nothing ever reaches across it to actually touch us. The light of distant stars arrives, yes, but it arrives gently, a whisper you need a telescope to even notice. This was different. This dead star reached out across 50,000 light years and physically nudged our atmosphere, and it did it in 1/5 of a second. Up in orbit, our spacecraft felt it even more strongly than the air did. We had at the time a whole fleet of telescopes circling the Earth, machines built specifically to watch the high-energy sky, to catch X-rays and gamma rays that never make it down to the ground. They had names, these machines. There was one called RESI and one called SWIFT, and one called Integral, and a set of detectors called Conus Wind riding along on various satellites. They were designed to be sensitive, to catch faint flickers from the distant universe, and when the flare hit, it didn't just register on them, it overwhelmed them. It saturated their detectors, flooding them so completely that the instruments simply couldn't keep up. The way your eyes are blinded for a moment if someone flicks on a bright light in a dark room. These were machines built to stare at the most violent objects in the cosmos, and a single flare from one dead star 50,000 light-years away was bright enough to dazzle them all at once. The most sensitive eyes humanity has ever lifted into space, briefly blinded by a corpse of a star on the far side of the galaxy. So that's where we begin tonight, with that flash. With the strangeness of it, the scale of it, the way something so far away could still come and touch the air above us. But here's where it gets stranger, and here's the promise I want to make you for the rest of the night, the thing that will carry us through all of this, that giant flare, that 250,000 years of sunlight in a fifth of a second, all of it came from the magnetism of this dead star. From its magnetic field, the strongest magnetic field anywhere in the known universe. And I know what magnetism sounds like. It sounds small. It sounds like the fridge magnet holding up a child's drawing, or the soft click of a cabinet door, or a compass needle swinging lazily to find north. Magnetism, in our everyday lives, is a gentle, almost cozy force. It's the faint tug you feel when you bring two magnets close and they want to snap together. It's harmless. It's a toy. You've probably heard somewhere the fun little fact that gets repeated about these objects, that a magnetar's magnetic field is so strong it could wipe the magnetic strip off a credit card from halfway to the moon. And it's a wonderful image, isn't it? Picture it. A bank card floating in space 100,000 kilometers out, and from that distance, with nothing touching it, the information simply erased, the little black strip wiped clean by a force reaching across all that empty space. People love that fact. It gets passed around. It makes the whole thing feel playful and almost cartoonish, like a magic trick performed across the void. But here's the thing I want you to hold on to as we drift off tonight. That credit card trick, that wiping of a card from halfway to the moon, is the gentle end of what this thing's magnetic field does. So that's the soft version. That's the part we tell at parties. The truth of what this field does up close is so much stranger and so much more profound that the credit card line will start to feel almost quaint by the time we're through. We'll get there, slowly. We're going to walk all the way up to this dead star carefully and find out exactly what its magnetism really means and how, on Earth, how in the whole universe, a dead star ends up this magnetized in the first place. Because the origin of all this impossible power, turns out to be one of the genuine open mysteries of modern physics. Even now, the people who study these things don't fully agree on how it happens. But no rush. We have all night, and you have all the time in the world to fall asleep before we get to the bottom of it. The answers will keep. So let's slow right down, and before we go any further, let's get a picture in our minds of what this object even is, because to understand its magnetism, you first have to understand what kind of thing we're talking about, and it is a very, very strange kind of thing.
I keep calling it a dead star, and I want to explain what I mean gently, because it's one of the most beautiful and unsettling ideas in all of astronomy.
Stars, like everything else, don't live forever. A star is a long, slow act of burning. Deep in its core, under crushing pressure, it fuses lightweight elements into heavier ones, and that fusion releases energy, and that energy pushes outward, holding the star up against the relentless inward pull of its own gravity. A star is a balance, really. A truce. Gravity wants to crush it down into nothing, and the heat of the fusion in its heart pushes back out, and for millions or billions of years, those two forces hold each other in a steady, glowing standstill. That balance is the star's whole life. That standstill is what a star is. But the fuel doesn't last. Eventually, deep in the core, the star runs out of things to burn, and when the fire in the center goes out, the truce breaks. There's nothing left pushing outward, nothing holding gravity back, and so gravity finally gets its way. The core collapses. For the biggest stars, the truly massive ones, 10, 15, 20 times the mass of our Sun or more, this collapse is sudden and catastrophic. The core falls in on itself in a fraction of a second, and the outer layers of the star come crashing down behind it, and then rebound in a colossal explosion that we call a supernova. For a few weeks, that single dying star can shine brighter than its entire host galaxy, brighter than 100 billion ordinary stars combined. It's one of the most violent events the universe knows how to produce, the death of a giant. And in the heart of that explosion, where the core fell in, something is left behind, a remnant, a small, dense, dead thing, all that's left of a star that once blazed across the cosmos. And depending on exactly how massive the original star was, that remnant is one of the strangest objects in all of nature. Sometimes it's a black hole, but for a certain range of stars, what's left behind is something called a neutron star. And a magnetar, the thing we're talking about tonight, the strongest magnet in the universe, is a particular, especially extreme kind of neutron star. So let me tell you about neutron stars, because once you understand how absurd they are, everything that follows becomes a little easier to believe. When that stellar core collapses, gravity squeezes it with a force almost beyond comprehension. It squeezes so hard that the ordinary structure of matter simply gives way. You see, everything around you, your blanket, your hand, the air you're breathing, is made of atoms, and atoms are almost entirely empty space. There's a tiny, dense nucleus in the center, and then a vast, vast emptiness around it where a few electrons drift in a faint cloud. If you could blow an atom up to the size of a great cathedral, the nucleus in the middle would be smaller than a grain of sugar. Almost everything is that emptiness. The solidity of the world, the firmness of the chair you're sitting on, is really just the electric pushback of those electron clouds refusing to overlap. We live in a world that is mostly nothing, held apart by tiny forces. But in the collapse of a dying star's core, gravity overpowers all of that. It crushes the emptiness right out of the atoms. The electrons are forced down into the nuclei, and they merge with the protons there, and what's left is a sea of neutrons, packed together with no gaps at all, no emptiness between them, just one solid, continuous, unimaginably dense mass. That's where the name comes from. A neutron star. A star made almost entirely of neutrons, packed shoulder to shoulder with nothing in between. And the density that results from this is the thing I most want you to feel as you drift off tonight, because it's genuinely one of the most astonishing facts in all of science. A neutron star takes more than the entire mass of our Sun, around 1.5 times the Sun's mass, and packs it into a sphere only about 20 kilometers across. 20 kilometers, that's it. That's the size of a city. You could drive across it in 20 minutes on an ordinary road, if such a thing existed. More than the mass of the Sun, a thing so large you could fit 1 million Earths inside it, all crammed down into a ball no bigger than the town you live in. This is described in the work of 2 scientists, Latimer and Prakash, who study exactly these objects. I find that almost impossible to hold in my mind, so let me give you a smaller way in. Let me give you a sugar cube. Imagine a single small cube of this neutron star material, just 1 centimeter on each side, the size of a sugar cube you might drop into your tea. Picture it sitting in the palm of your hand. It's small, it's nothing. It would fit between 2 of your fingers. And that one little cube, that sugar cube of neutron star matter, would weigh something like 100 million tons. Some estimates run all the way up to 1 billion tons, one sugar cube, weighing as much as a small mountain, as much as all the cars in a great city stacked together, all of it pressed into a thing the size of a sugar cube, sitting in your open hand. Of course, you couldn't actually hold it. Long before it touched your skin, it would tear straight through your hand and through the floor and down into the earth, because nothing we know of is strong enough to support that kind of weight. But the image is the thing, a sugar cube that weighs 1 billion tons. That's what this dead star is made of all the way through, a whole city-sized ball of it, packed denser than the nucleus of an atom, spinning silently in the dark. So already, before we've even gotten to the magnetism, before we've gotten to the field that wiped at our atmosphere from 50,000 light-years away, we have one of the strangest objects imaginable, a dead star, the crushed-down core of a giant that exploded long ago, a city-sized ball holding more than the mass of the sun, so dense that a single spoonful of it outweighs a mountain, spinning out there in the cold, dark quiet of space, exactly where the supernova left it, thousands of years ago, maybe tens of thousands. And it just sits there, this impossible thing, going about its strange existence, whether or not anyone is watching. Most of them we never see. They're tiny by cosmic standards, just 20 kilometers across, in a galaxy 100,000 light-years wide. They give off almost no ordinary light. They're dead, after all. The fire that once held them up against gravity went out a long, long time ago. In a sense, they're the ash left over from a fire that consumed an entire star. Cinders, embers, the dark, dense remains of something that used to blaze. And yet some of these cinders, a rare few of them, carry inside them the most powerful magnetic field anywhere in the known universe. Strong enough to disturb the air of a planet from across the galaxy. Strong enough to wipe a credit card from halfway to the moon, which, remember, is only the gentle end of what it does. Strong enough to do things to matter and to light and to the empty vacuum of space itself that no laboratory on Earth could ever come close to reproducing. Things that sound less like physics and more like a strange dream. That's what we're going to drift through together tonight. Not just the fact that it's the strongest magnet in the universe, but how that's even possible. How a dead, cold cinder of a star ends up holding a magnetic field that puts everything else in the cosmos to shame. And the honest, beautiful truth is that even the scientists who have spent their whole lives studying these things are still not entirely sure how it happens. There's a leading idea and a rival idea and a real, ongoing debate, and we'll wander gently into all of it, in no particular hurry at all. But for now, just hold the picture. A dead star, 20 kilometers wide, heavier than the sun. A sugar cube of it weighing 1 billion tons. Sitting 50,000 light-years away in the crowded heart of the galaxy, silent and dark and almost invisible. And wrapped around it, threaded through it, woven into every part of it, the strongest magnet in the universe, waiting. Now let's get a little closer to it now, slowly, and start to understand just how strong that field really is. Not in vague words, but in real numbers, in things you can picture, in fridge magnets and compass needles and the most powerful machines we've ever built. Because once you see the scale of it laid out gently next to the ordinary magnets of your everyday life, you'll start to understand why this object is in a category all its own, and why getting too close to it would be one of the strangest ways imaginable to come to harm. So take a slow breath Let your shoulders drop a little further into the bed. There's nothing you need to do, nowhere you need to be. The dead star will still be there, 50,000 light years away, spinning in the dark, holding its impossible field, whether you're awake to hear about it or already halfway into a dream. And let's keep going gently into just how strong this strongest of all magnets truly is. Start with something you already know, a fridge magnet. The little one holding a photo or a takeaway menu to your kitchen door. It's about 100 gauss. Gauss is just the unit we use to measure how strong a magnetic field is, and 100 of them is enough to grip a sheet of paper against metal, but not much more than that. You can pull it off with 2 fingers without even thinking about it. That's the kind of magnet you live with every day, the kind so gentle you forget it's a magnet at all. Now climb up a little. Picture the Earth itself, the whole spinning planet under you, with its molten iron core slowly churning and generating the field that makes a compass needle swing north. That field, the one that has guided sailors for centuries and keeps the solar wind from stripping our air away, is about half a gauss. Half. The entire planet, and its magnetic grip is weaker than the little magnet on your fridge. It's just spread out across the whole globe, faint and wide, enough to nudge a needle, but nothing you'd ever feel. Climb higher. Go into a hospital, into one of those big machines that takes pictures of the inside of your body. An MRI scanner, that's a serious magnet, a strong one, runs somewhere between 30,000 and 70,000 gauss. That's why they tell you to leave your watch and your keys and anything metal outside the room. That's a field that can pull a wheelchair across the floor, that hums and clicks and fills a whole room with its pull. 30,000 gauss. Hold that number for a moment because it already feels enormous next to your 100 gauss fridge magnet, doesn't it? And we're not done climbing, not even close. Think about the strongest magnets human beings have ever built. Not the everyday ones, but the giants. The ones in laboratories where people spend their careers trying to push magnetism as far as it will go. The strongest, steady, continuous magnets we can make reach around 45 Tesla. And here we switch units just for a breath because Tesla is the other word scientists use, and 1 Tesla is 10,000 gauss. So 45 Tesla is around 450,000 gauss. That's the strongest sustained magnetic field a person has ever held in a machine. And if you let go of steady and allow a brief, violent, destructive pulse, the kind that tears the apparatus apart in the instant it fires, you can reach something like 1200 Tesla for a fraction of a moment before the whole thing blows itself to pieces. That is the absolute outer edge of what we can do. The ceiling of human magnetism reached only by destroying the very machine that makes it. Now hold all of that in your mind at once. The fridge magnet, the whole Earth, the MRI scanner, the most powerful machine we've ever built, fields so strong they shatter their own walls. Line them up gently like a row of stepping stones, and then go to the dead star. A magnetar's field at its surface reaches somewhere between 10 to the 14 and 10 to the 15 gauss. I know those numbers don't mean much spoken out loud, so let me lay them next to the others. It's roughly a quadrillion times stronger than the Earth's field. A quadrillion, a 1 with 15 zeros after it. And it's 100 million to a billion times stronger than any magnet we have ever managed to build, even the ones that destroy themselves in the making. Take the strongest thing humans have ever done with magnetism, the field that rips a laboratory apart, and you would have to multiply it 100 million times, maybe a billion, just to reach the surface of this object. There's a catalogue of these things, the Magnetar catalogue, where astronomers keep careful track of every confirmed one and the field strength they've measured. And at the very top of that scale, sitting at the strongest end, is the same object that lit up our sky in 2004. SGR 1806-20, right out there at 10 to the 15 gauss, the most magnetic thing we've ever measured anywhere in the known universe. And here's a quiet thought to fold into that. The field we measure is only the surface field, the part that reaches out into space where our instruments can read it. Some scientists who model the insides of these stars think the field looped and twisted within the body of the magnetar may be even stronger than the one we see on the outside. A hidden field coiled inside the crust, more powerful than the already impossible thing we can detect. We're measuring the outer edge of something whose true heart we can't directly see. So let that settle for a moment. The strongest magnet in the universe, and we may only be looking at the gentle outside of it. Now you might be wondering what a field like that would actually do. And this is where I have to be careful with you, because the popular stories about magnetars love to exaggerate this part, and I'd rather give you the real picture, which is strange enough on its own without any embellishment. You may have heard the line that a magnetar could wipe the magnetic strip off a credit card from halfway to the moon. And there's truth in that, in a rough, order of magnitude way. Robert Duncan, one of the two physicists who gave these objects their name, used that very image to help people feel the scale. Somewhere out around 100,000 kilometers, a fair fraction of the way to the moon, the field would still be strong enough to scramble the little stripe of magnetism on a card in your wallet. It's a vivid picture, and it's meant as an illustration rather than a precise measurement, so hold it loosely. But here's the thing I really want you to notice, the thing the spooky version always skips. That credit card distance is the gentle end, that's the soft edge of what this field does. The wiping of a card from 100,000 kilometers away is the magnetar being polite. Because if you came closer, much closer, the field would stop merely erasing things and start unmaking them. And we'll get there slowly to that 1,000-kilometer line where the danger changes from a parlor trick into something that reaches into the very atoms of your body. But not yet. There's no rush. I just want you to carry that one idea into the dark with you, that the scariest stories you've heard about this object are describing the kindest thing it can do. For now, just sit with the scale of it. A field a quadrillion times the Earth's, 1 billion times the strongest machine we've ever built. So strong that the inside may be fiercer still than the surface. So strong that even from 100,000 kilometers away, it can reach into your pocket and rewrite the magnetism on a piece of plastic. And all of it wrapped around a ball of dead star only 20 kilometers wide, the collapsed core of a giant that ran out of fuel and fell in on itself long ago. That's the object. That's the strongest magnet in the universe. A city's width of impossible density, heavier than the sun, spinning slowly in the dark, holding a field that bends the rules of everything around it. And the question that should be growing in your mind now, the one we'll spend the rest of our slow journey trying to answer, is a simple one. Where did a field like that even come from? How does a dead star, the burnt-out core of something that's already finished living, end up holding the most powerful magnet in all of existence? Because a magnet doesn't just become a quadrillion times stronger than a planet by accident. Something has to make it that way. Something has to build a field that monstrous and then freeze it in place. And the strange, wonderful truth is that even now, the people who study these objects more closely than anyone alive can't fully agree on the answer. So let's spend some time with the numbers. Not to show off, not to drown you in units you'll forget by morning, but because the numbers are the only honest way to understand what makes a magnetar different from every other magnet that has ever existed. And when you see them laid out side by side slowly, something clicks into place that no amount of verbal description can quite achieve on its own. Start somewhere familiar. The fridge in your kitchen or wherever you happen to keep yours very likely has a magnet or two stuck to its door. A shopping list. A photograph. Maybe a souvenir from somewhere you traveled years ago. Those magnets are doing real work, and their fields are somewhere in the range of 100 gauss. That is the unit we use to measure magnetic field strength, the gauss, named after the German mathematician and physicist Carl Friedrich Gauss, who did foundational work on the theory of magnetism in the 19th century. 100 gauss. It sounds like a number without meaning until you put other numbers next to it. Step up to something more serious. A hospital MRI machine, the kind that makes a thunderous knocking sound and asks you to hold very still, generates a magnetic field of somewhere between 30,000 and 70,000 gauss. Between 3 and 7 Tesla in the other common unit named after Nikola Tesla, that field is strong enough that radiologists post signs outside MRI suites warning people not to bring anything metallic inside because the machine will pull ferromagnetic objects toward itself with violent, sometimes dangerous force. People have accidentally walked metal chairs into active MRI rooms and had the chair ripped from their hands and launched across the space. That is 30,000 gauss at its lower end, a field you can feel with your whole body. Now go further. The most powerful continuous magnets human beings have ever built, the ones that require engineering so precise and expensive that only a handful exist in the entire world, top out at roughly 45 Tesla. That is 450,000 gauss. They are sustained magnets, meaning they hold that field continuously without destroying themselves. There are also pulsed magnets, the kind that fire for a fraction of a second and are then briefly inoperable, and those can reach something closer to 1200 Tesla in a destructive pulse, a field so intense the magnet is essentially consuming itself to generate it. 1200 Tesla, more than 1,000,000 gauss, the most extreme conditions any laboratory on Earth has ever produced by deliberate human effort. Hold those numbers: 100 gauss on your fridge door, 30 to 70,000 gauss in a machine that costs millions and occupies its own reinforced room, 45 Tesla, 450,000 gauss at the absolute outer edge of what our best continuous engineering can sustain. And Earth itself, the planet you are lying on right now, generates a magnetic field of about half a gauss at its surface. That's what a compass needle follows, half a gauss, produced by the slow churning of liquid iron thousands of kilometers beneath your feet, a dynamo the size of a world that has been running for billions of years. Now, a magnetar. The surface magnetic field of a magnetar sits somewhere between 10 to the 14th and 10 to the 15th gauss. That is between 100 trillion gauss and 1,000 trillion gauss. In Tesla, that is 10 billion to 100 billion Tesla. Those are the numbers compiled in the McGill Magnetar catalogue and confirmed across the field's literature, including the comprehensive 2017 review by Victoria Caspi and Andrei Beloborodov in the annual review of astronomy and astrophysics. Two are the people who have spent their careers working on these objects, and those are the numbers they stand behind. Let's turn that into comparisons your sleeping mind can actually hold. A magnetar's field is roughly a quadrillion times stronger than Earth's. A quadrillion, that is a 1 followed by 15 zeros. If you wanted to make the Earth's magnetic field into a magnetar field, you would have to multiply it by 1,000 million million. And yet the Earth's field is the thing that guides migrating birds and keeps compass needles pointing north, the field that shields us from the solar wind. A magnetar field leaves that behind the way a bonfire leaves a birthday candle behind. Compared to the strongest continuous magnet human beings have ever built, a magnetar is roughly 100 million to 1 billion times stronger. Not twice as strong, not 1,000 times as strong, 100 million to 1 billion times stronger. The most extreme thing our physics and engineering and materials science can produce, the thing that requires superconducting coils and cryogenic cooling and purpose-built buildings, is to a magnetar what a candle is to the sun. Less, actually. The fractions involved would shame a candle, and compared to that fridge magnet holding up your shopping list, the magnetar is somewhere around a 10 to the 13th multiple, 10 trillion times stronger than the thing that occasionally drops your grocery list on the floor. Now here's the thing about numbers this large. They stop being numbers in any ordinary sense. They become more like a flag, a marker saying, here, at this location, Something is happening that ordinary physics cannot describe. The rules change, and I want to spend a moment with that because it matters enormously for understanding what a magnetar actually does to the space and matter around it. There are two distances you will often hear mentioned when people talk about the destructive reach of a magnetar. And these two distances get confused with each other constantly in popular accounts, blurred together into a single, vague, deadly field description that misses something important about how the physics actually works. So let's take them apart, slowly, one at a time. The first distance, and the one that comes up in the context of the video's title, is the credit card distance. This is the range within which a magnetar's field would still be strong enough to erase the magnetic strip on a credit card. It is a large distance, roughly halfway to the Moon. The Moon orbits Earth at an average distance of about 384,000 kilometers, so halfway there is somewhere in the neighborhood of 100 to 200,000 kilometers. This figure has been associated with Robert Duncan himself, one of the physicists who first predicted that magnetars could exist, using it in public outreach to convey the extraordinary reach of the field. It is an illustrative number, an order of magnitude illustration, rather than a precision measurement from a laboratory, but it comes from a credible source and it is doing a real job. It is showing you that a magnetar's field is not a local phenomenon. It reaches. It extends out into space at enormous distances and still does things to matter, still rearranges the information stored in magnetic materials. A credit card's magnetic strip works by having small magnetic domains aligned in particular patterns that encode your account information. A sufficiently strong external field can disrupt those alignments, scrambling the data. At roughly halfway to the Moon, a magnetar's field is still strong enough to do that, to reach across that void and disorganize the tiny magnets on a piece of plastic. If you could somehow hover a credit card at that distance from a magnetar, it would come back unreadable. That is remarkable. But here is where the popular accounts typically go wrong. The credit card erase distance and the kill you with magnetism distance are not the same distance, not even close. They differ by 2 orders of magnitude, meaning a factor of 100 roughly. And mixing them up is the difference between an accurate picture of an extraordinary object and an overstatement that makes the universe seem more melodramatically dangerous than it is. The genuinely lethal magnetic radius, the distance at which the field itself, through purely magnetic effects, would begin to destroy a human body or any matter made of ordinary atoms, is approximately 1,000 kilometers, not 100,000 kilometers. 1,000. Here is what happens at that range, and the physics of it is worth sitting with for a moment because it is genuinely strange. Atoms, as you probably know in a general way, consist of a nucleus with electrons moving around it. The electrons occupy what physicists call orbitals, regions of space where they are likely to be found, and those orbitals have shapes, some spherical, some shaped like dumbbells or more exotic forms. The chemistry of all matter, including the chemistry of your body, including the biochemistry that makes your proteins fold correctly and your DNA replicate and your neurons fire, depends on the shapes of those electron orbitals and the angles at which atoms bond to each other. A magnetic field strong enough to approach the quantum critical field, what physicists call the Schwinger limit, at roughly 4.4 times 10 to the 13th Gauss, does something extraordinary to those electron orbitals. It begins to dominate the behavior of the electrons. The electrons, which normally move in those characteristic orbital shapes, start to be constrained by the field lines. Their orbitals get squeezed, compressed, elongated into thin cylinders aligned along the direction of the field. The shapes that determine all of chemistry start to change. This happens gradually as the field strength increases, and at the surface field strengths of a magnetar, 10 to the 14th or 15 Gauss, you are already past the Schwinger limit, well past it. The quantum electrodynamic effects are not subtle corrections here. They dominate. An atom in a field that strong does not look like an atom in the way we normally think of one. It has been deformed by the magnetism into something narrower and more elongated, the electron cloud pulled along the field lines like taffy, the chemical bonds it can form completely different from what they would be in ordinary conditions. For a human body at roughly 1,000 kilometers from a magnetar, the field would be strong enough to begin doing this to every atom in your body simultaneously. Every hydrogen atom in your water molecules, every carbon atom in your proteins, every atom in every structure that keeps you alive. The chemistry that keeps you assembled would start to fail, not because the magnetar is touching you, not because it is radiating heat or hard radiation at you from that distance, but because its magnetic field alone at 1,000 kilometers is strong enough to reach in and rearrange the geometry of the matter you are made of. That is what Harding and Lai laid out in their 2006 work in Reports on Progress in Physics on the quantum electrodynamics of these extreme field environments, and it is the figure that NASA's Goddard Educational Materials use when they describe the lethal field radius of a magnetar. 1,000 kilometers, not halfway to the moon. 1,000 kilometers, which is still, to be completely honest, a staggering distance for a purely magnetic effect to propagate. But it is very different from 100,000. When you hear someone say a magnetar would kill you from halfway to the moon, they are either confused about the two distances or they are gesturing at a different kind of harm. The radiation, the X-rays and gamma rays a magnetar constantly emits, which reach far further and at much smaller doses can certainly be harmful. But the pure magnetic destruction of your atomic structure, the field doing to your atoms what it does to atoms near the quantum critical field, that begins at 1,000 kilometers. The credit card wipes at 100,000. Those are the two radii. Keep them separate and you have an accurate picture. Blur them and you have something scarier sounding but less real. And even the 1,000-kilometer kill radius, dramatic as it is something you can sit with calmly tonight because of a fact we will come back to properly before this is over. The nearest known magnetar to Earth is thousands of light years away. 1 light year is about 9.5 trillion kilometers. Thousands of light years away means the nearest one is so far off that even its most violent giant flares, like the one on December 27, 2004, barely brush the outer edge of our atmosphere and cause no harm whatsoever at the surface. But we'll come to that in full. For now, just hold the two radii as two distinct things and know that the picture is precise enough to be trusted. Right. So you have a sense of the numbers now and of what those numbers mean for matter and chemistry and atomic structure. Let's pivot, because there's something else about magnetars that needs to sit alongside the field strength before we get to the question of where the field came from, something about how these objects are powered, because this is where magnetars diverge from their closest relatives in a way that changes everything. Neutron stars that emit pulses of radiation, the ones we call pulsars, are extraordinary objects in their own right. They rotate fast, many of them, some spinning hundreds of times a second, and they carry magnetic fields that are themselves impressive by any normal standard, though nothing like a magnetar. The way an ordinary pulsar radiates, the way it sends out beams of energy we can detect, is fundamentally rotation-powered. Think of it a little like a dynamo on a bicycle wheel, the kind that used to power a lamp on older bikes. As the wheel spins, it generates electricity, and the faster it spins, the brighter the light. A pulsar is doing something analogous at an extreme scale. It is converting rotational kinetic energy, the energy stored in the fact that it is spinning, into electromagnetic radiation. As it radiates, it gradually slows down. The spin bleeds away. If you measure a pulsar carefully over time, you can detect that its rotation is decelerating, and from that deceleration, you can work out how fast it is losing energy. Magnetars do not follow that pattern in any consistent way. and for a long time this was one of the things that marked them as genuinely strange. A magnetar typically rotates much more slowly than an ordinary pulsar. Rotation periods of 2 to 12 seconds are common, which in neutron star terms is leisurely, even sluggish. An ordinary pulsar can be spinning 30 or 100 or several hundred times per second. A magnetar might spin once every several seconds, and yet a magnetar produces bursts of energy so enormous that even the most energetic ordinary pulsars cannot compete. The energy output during a major burst vastly exceeds what the slow rotation could supply. If you do the calculation, if you add up the energy that should be available from a slowly spinning neutron star and compare it to the energy coming out of a magnetar during an outburst, the numbers do not balance. The spin is simply not the fuel. Victoria Caspi and Andrei Beloborodov, in that 2017 annual review paper, are clear about this. The persistent X-ray luminosity of magnetars often exceeds what their rotation could power, and the burst energies are far beyond it. The only source large enough to account for what magnetars are doing is the magnetic field itself. The field is the fuel. This is a profound thing to sit with for a moment. The magnetic field of a magnetar is not just a property of the object, not just something wrapped around it like an atmosphere. It is the energy reservoir that the entire outburst activity draws from. When a magnetar produces a burst, what it is ultimately doing, on the deepest level, is converting some of the energy stored in its magnetic field into radiation. The field is decaying very slowly, releasing that stored energy, and the quantity of energy stored in a field that's strong around an object that compact is almost incomprehensibly large. This also means something interesting about what happens over time. As the field decays, as that energy reservoir slowly drains over thousands and tens of thousands of years, the magnetar's outburst activity diminishes. It quiets down. The violent bursting phase lasts for roughly 10,000 years or so while the field is at its strongest, and the internal stresses it creates are still dynamically active. Then gradually, the field weakens. The object cools and quiets. Eventually, it becomes what is effectively a very hot, ordinary-looking neutron star with a somewhat stronger field than average, the storm over, the fury spent, the record of its extraordinary youth buried in physics we can no longer easily read. Most neutron stars in the galaxy that were once magnetars are probably dormant now, living quiet afterlives, no longer announcing themselves with giant flares, invisible to most of our detection methods, drifting through space as unremarkable seeming dead stars. The McGill Magnetar Catalogue, which is the authoritative ongoing record of these objects maintained at McGill University and first formally published by Olausen and Caspi in 2014, lists only around 30 confirmed magnetars and a handful of candidates. 30 in a galaxy of hundreds of billions of stars. Not because magnetars are born rarely necessarily, but because their active window is so brief on cosmic timescales that at any given moment only a small fraction are in their loudly announcing phase. The galaxy may hold millions of dormant magnetars we simply cannot easily detect. Sleeping giants scattered through the dark. So, slowly rotating, not spin-powered, burning through their magnetic field as fuel, active for a cosmically brief window, then quiet. That is the operating picture. That is how a magnetar lives and ages. But here is the question that should have been sitting at the back of your mind through all of this, the question that the whole dossier is organized around answering, the question the title of tonight's video actually promises to address. And it is the most important question about these objects, the one that even now does not have a fully settled answer. Where did the field come from? A fridge magnet has a field because the iron atoms in it are aligned by a manufacturing process that sets their magnetic moments in the same direction. A bar magnet has a field because the small magnetic domains in the iron have been arranged to point the same way. Earth has a field because liquid iron in its outer core is churned by the planet's rotation into a slow, self-sustaining dynamo. Every magnet you have ever encountered has a story about how its field was created and maintained. A magnetar has a field a quadrillion times stronger than Earth's. That field did not arise from nowhere. Something made it. Something amplified it to that extraordinary level. And the question of what exactly is one of the genuinely open problems in astrophysics. There are two main hypotheses, and I want to walk you through both of them gently and clearly, because neither one is obviously right. And the honest position, the one taken by serious researchers in the field, is that the answer might be a combination of the two, or something we haven't fully worked out yet. The first hypothesis, and the one that came earliest and has attracted the most theoretical development, is called the convective dynamo hypothesis. It is most closely associated with Robert C. Duncan and Christopher Thompson, who in 1992 published the paper in the Astrophysical Journal Letters that first predicted that objects like magnetars could exist and coined the term magnetar for them. They followed this with another paper in 1993, Thompson and Duncan, developing the dynamo mechanism in more detail. Here is the central idea. When a massive star, something between roughly 10 and 25 or more solar masses, reaches the end of its life, it runs out of fuel for fusion in its core. The core collapses. This happens extraordinarily fast, on a time scale of fractions of a second, a catastrophic gravitational implosion that compresses material far denser than any ordinary matter. What is left is a neutron star, an object so dense that the protons and electrons of atoms have been pressed together into neutrons. But right at the moment of birth, in the first seconds after the collapse, the neutron star is not yet the cool, settled object it will eventually become. It is extraordinarily hot, extraordinarily turbulent, and, in some cases, extraordinarily fast spinning. Duncan and Thompson's critical insight was this: if that newborn neutron star is spinning fast enough on a timescale of about 1 millisecond, 1 revolution per millisecond, and if it is hot enough to be violently convective, meaning its interior is boiling in a turbulent, churning way rather than settling into calm layers, then you have all the ingredients for a dynamo. A magnetic dynamo works, in simplified terms, by having a conducting fluid moving in a complex, turbulent pattern in the presence of a seed magnetic field. The motion of the fluid stretches and amplifies the field lines, and if the conditions are right, the process becomes self-sustaining and the field grows. Earth's magnetic field is generated this way in the churning liquid iron of the outer core. The Sun's magnetic field is generated this way in its outer convective layer. But the newborn neutron star in Duncan and Thompson's model is running this process at extreme speed and in extreme conditions. The fluid is not liquid iron, but the densest matter outside a black hole. The convection is not gentle atmospheric overturning, but violent, fast, energetic churning driven by the massive temperature gradients in the first seconds of the star's existence. And if the spin is fast enough around that 1 millisecond mark, then the combination of rapid rotation and violent convection can amplify the seed magnetic field, the modest field that was already there from the progenitor star, by a factor of roughly 1,000 or more in the first 10 to 30 seconds of the neutron star's life. 10 to 30 seconds, that is the window in which, according to the dynamo model, a magnetar's field is created, an event so brief that a human would have barely had time to take 3 breaths, and yet the outcome is a magnetic field frozen into an object that will then carry it for tens of thousands of years. After those first seconds, as the neutron star cools and the convection slows, the dynamo process stops, but the field it created doesn't go away. It is locked into the structure of the star, frozen in place by the extreme density and conductivity of the neutron star material, which has an electrical conductivity so high that it would take an almost inconceivably long time for the field to dissipate, far longer than the current age of the universe in the deepest layers. The field is, in a real sense, permanent on any timescale that matters, written in the structure of the dead star like a message that cannot be erased. But, and this is where the honest uncertainty comes in, the dynamo model requires something specific, that the newborn neutron star was spinning very fast, around 1 millisecond per rotation. And here is the thing about that requirement. We don't always know why a collapsing stellar core would spin that fast. Most neutron stars we observe are not spinning anywhere near that quickly at birth. The 1 millisecond spin rate that the dynamo model needs is extreme, even by neutron star standards. Something has to give the newborn neutron star that specific initial spin, or the dynamo never gets going strongly enough to build a magnetar field. This is where the second hypothesis enters, and it has a different flavor entirely. The fossil field hypothesis, developed and argued by researchers including Ferrario and Wickramasinghe in work published in 2006 and reviewed more recently by Esposito and colleagues in 2021, takes a completely different approach to the same problem. Instead of asking how the field is built after the collapse, it asks whether the field was already there, in the progenitor star, before it died. Some massive stars are known to have strong magnetic fields, not magnetar strength, but genuinely strong by stellar standards. When such a star collapses, magnetic flux, which is a measure of the total amount of magnetic field threading through a surface, is approximately conserved. That is a fundamental result of the physics. If you squeeze something that has a magnetic field into a much smaller volume, the flux is concentrated and the field strength per unit area increases dramatically. A star that was strongly magnetized, compressed from a body roughly 1 million kilometers across to a neutron star only 20 kilometers across would experience a concentration by a factor of roughly 10 to the 9th, a billion. A modest stellar field of a few hundred gauss, strong for a star but nothing extraordinary, could in principle be amplified to near magnetar levels purely by this geometrical compression during the collapse. The fossil field hypothesis has the advantage of not requiring any special spin rate. The field is simply inherited, amplified by geometry. No dynamo needed, no millisecond spin needed, just collapse and conservation of flux. The disadvantage is that it requires the progenitor to already have a strong field, and we don't have direct evidence that all magnetar progenitors do, and the field distributions in the resulting neutron stars might look different under the two models. What the researchers are currently finding is that neither model alone seems to cleanly explain all the observations. The real picture may involve both processes contributing, or it may require modifications to both models, or it may require something about the collapse physics that we don't yet fully understand. Esposito and colleagues' 2021 review lays out the debate clearly and arrives at the honest conclusion. The origin of magnetar fields is genuinely unsettled. And there is something I find worth holding gently, something quietly remarkable about that state of affairs. We can measure the surface field of a magnetar to within an order of magnitude. We can catalogue its bursts, time its rotation, watch it disturb the ionospheres of planets from 50,000 light-years away. We know with precision what it does. We can describe what happens to atoms near it, what happens to light near it, what happens to the vacuum itself near it. And yet the question of exactly how it came to be the way it is, the mechanism by which a dying star wrote that extraordinary field into the structure of its own corpse, is still being worked out. That seems to me like exactly the right kind of mystery to carry into sleep. Not a scary one, not an unsettling one, just a genuinely open one, a place where the universe is still being patiently interrogated by the people whose work it is to ask. There is one more layer to the field story before we move to some of the stranger consequences of its existence, and it concerns what happens beneath the surface of the magnetar in regions no observation can directly gauge. What we measure when we characterize a Magnetars field, the 10 to the 14th or 15 gauss that goes into the McGill catalogue, is the surface dipole field. The field as it looks from outside in its simplest large-scale configuration. But there is strong theoretical reason to believe that the field inside a magnetar, buried in its interior, is more complicated and potentially stronger than what the exterior dipole measurement captures. Magnetic fields in astrophysics can take different geometrical configurations. The dipole, the simplest, is what you see outside a bar magnet, two poles, field lines arcing between them. But inside a conducting body, fields can also arrange themselves in what are called toroidal configurations, looping around the inside of the star in circles like a donut, rather than extending out through the surface. These toroidal internal fields are effectively hidden from external measurement. They do not contribute to the dipole signature we detect. And in some models of magnetar field evolution, the interior toroidal field may be significantly stronger than the external dipole field we can see. If that is right, and the models developed by researchers including Makarenko and others in crustal field modeling suggest it may be, then the numbers we quote for a magnetar's surface field strength are actually an underestimate of what the object is carrying inside. The real heart of the magnetic energy might be looped within the star, invisible, stronger than the face it shows to the galaxy. A secret, fiercer core beneath an already extraordinary exterior. That hidden depth makes the dynamo versus fossil field debate even more interesting because the two mechanisms might produce different internal field geometries, different proportions of dipole to toroidal field, different locations of the strongest regions. In principle, future observations might be able to distinguish between the two origin routes by probing the detailed structure of a magnetar's field in ways that current instruments cannot quite achieve. It is work that is ongoing, patient, careful, and unfinished, and so that is the field. In numbers, in radii, in mechanism, in mystery. A surface field between 10 to the 14th and 10 to the 15th Gauss, a quadrillion times Earth's, 100 million to 1 billion times our best laboratory magnets. A field that kills by distorting atomic geometry within 1,000 kilometers, but can reorganize a credit card's magnetic strip from halfway to the moon. Two radii that popular accounts conflate, but that are genuinely different things. A field not powered by the star's spin, as in ordinary pulsars, but fed by the field itself as it slowly, irreversibly decays over 10,000 years. A field created either by a violent convective dynamo in the first 10 seconds after collapse, needing a millisecond rotation rate to run, or inherited as a fossil field from a strongly magnetized progenitor and concentrated by the geometry of collapse, or some combination of both that we have not fully resolved, and a field that may be fiercer in its hidden interior than anything it shows on its surface. So now you know the field exists, you know its numbers, you know it kills and reorganizes and bends the behavior of light itself. But the deeper question, which is the one the title quietly promises, is still sitting there, unhurried, waiting. How does a dead star end up this magnetized? That question doesn't have a single, tidy answer. And I think there's something genuinely comforting in that if you're the kind of person who finds comfort in honesty. The universe hands us this extraordinary object, this city-sized thing with a field a quadrillion times Earth's, and when we ask where it came from, the physicists who study it most closely say, we think we know mostly, but not entirely. The mechanism is partly understood, partly argued, and partly still hidden in the same interior we cannot see. That is not a failure of science. That is science doing exactly what it should, going right up to the edge of what it knows, planting a flag and admitting the edge is real. Let's go back, way back, to before the magnetar existed at all. Picture a star, not a small, placid, middle-aged star like our Sun, which will live for another 5 billion years and die quietly, expanding into a red giant, puffing away its outer layers, leaving a cooling white dwarf behind. No, this is a different kind of star entirely, something far more massive. We are talking about a star somewhere between 10 and 25 or more times the mass of the Sun, maybe considerably more, as we'll see before the night is through. These stars burn ferociously. They consume their hydrogen fuel in millions of years rather than billions. They are profligate, extravagant, almost reckless, enormous furnaces that spend everything they have as quickly as they can. And because they are so massive, they don't stop when they run out of hydrogen. They keep going. They fuse helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon. Each successive fuel burns faster and hotter. The silicon burning phase near the end lasts only a day or two. By the time the core has built up a ball of iron, the star is out of options. Iron is the end of the road. You cannot release energy by fusing iron into anything heavier. It costs energy rather than releasing it. And so the core, this ball of iron the size of Earth, compressed unimaginably tight, sitting at the center of a star so large it would swallow the orbit of several planets, it collapses. In less than a second, the iron core goes from the size of Earth to the size of a city, about 20 kilometers across. That is the neutron star being born. The collapse happens because the electrons that were holding the iron atoms apart, through what physicists call electron degeneracy pressure, the quantum mechanical resistance of electrons to being squeezed too close together, can no longer support the weight above them. They are overwhelmed. The protons and electrons in the core are forced together, merging into neutrons, releasing vast floods of neutrinos in the process, and the collapse stops only because the neutrons themselves push back. Neutron degeneracy pressure, a new flaw held up by the laws of quantum mechanics, preventing the collapse from going all the way to a black hole, at least for a star in this mass range. The outer layers of the star, still falling inward at a significant fraction of the speed of light, smash into this suddenly rigid neutron core and bounce. The resulting shockwave, powered by an almost incomprehensible torrent of neutrino energy, blows the star apart. This is the supernova, the explosion that for a few weeks can outshine an entire galaxy of hundreds of billions of stars. The light and heat and pressure wave that expands outward for centuries, eventually forming the glowing shells we call supernova remnants. Beautiful, delicate-looking structures visible through telescopes across thousands of light years. What remains at the center when the explosion has passed and the remnant is drifting outward is the neutron star, dense beyond ordinary imagination. A sugar cube of its material weighing somewhere between 100 million and 1 billion tons. More than the Sun's mass, roughly 1.4 solar masses, compressed into a sphere 20 kilometers across. Gravity at its surface is around 200 billion times what you feel sitting wherever you are tonight. The escape velocity from its surface is about half the speed of light, and it is spinning. This is important. This is, in fact, perhaps the most important thing in the story of how a magnetar gets its field. So let's stay with it for a moment. When the core collapses, angular momentum is conserved. This is the same principle that makes a spinning ice skater pull in her arms and spin faster. As the rotating mass gets smaller, the rotation rate goes up to compensate. The original iron core was rotating slowly, turning perhaps once every several hours or days as part of the spinning star. But when it shrinks from the size of Earth to the size of a city in under a second, that rotation rate increases enormously. The numbers work out, in some conditions, to a newborn neutron star rotating once every millisecond, 1,000 times per second. An object more massive than the Sun, 20 kilometers across, spinning 1,000 times per second. Not every neutron star is born spinning this fast. The initial spin depends on how much angular momentum was in the collapsing core, how the collapse proceeds, how the explosion and the explosion's asymmetries play out. Most neutron stars, it seems, are born with somewhat longer rotation periods, but some, in the right conditions, may come out rotating extraordinarily fast. And for the magnetar origin story, that extreme early spin rate matters enormously. Here is where Robert Duncan and Christopher Thompson enter the picture. Duncan and Thompson were working together in the early 1990s, thinking carefully about neutron stars and their magnetic fields. In 1992, they published a paper in the astrophysical journal Letters that proposed something new. A class of object that hadn't been confirmed yet, an object whose existence they were predicting from the physics. They gave it the name magnetar.
And the mechanism they proposed for how it got its extraordinary field is called the convective dynamo. The word dynamo will be familiar to you in a different context. Earth has a dynamo too. The molten iron in Earth's outer core convecting and circulating as the planet rotates, generates and sustains our planet's magnetic field. The sun has a dynamo.
The motions of hot, electrically conducting plasma in the solar interior, driven by convection and shaped by rotation, give the sun its complicated, shifting, powerful magnetic field. A dynamo, in the most general sense, is a process by which the motion of an electrically conducting fluid, or plasma, or even the semi-fluid hot matter in a newly born star, converts kinetic energy into magnetic energy. Moving charge generates a magnetic field. If you set up the right geometry of motion, you can make those fields reinforce each other and grow. Now, a newborn neutron star in the first seconds after the collapse is not yet the cold, rigid object it will eventually become. It is extraordinarily hot. Temperatures of hundreds of billions of degrees, it is, in those first moments, a roiling, boiling, churning sphere of neutron-rich matter and neutrinos. The neutrinos are streaming out in a torrent, carrying energy with them as they go, and this outward energy flow drives convection. Hot material rising, cooler material sinking, enormous, churning loops of motion happening throughout the star's interior. Duncan and Thompson realized that this convective motion happening inside an object that is both an extraordinarily good conductor of heat and electricity and rotating at tremendous speed is exactly the recipe for a dynamo. The key insight is this: if the newborn neutron star is rotating fast enough, rotating with a period close to 1 millisecond, then the Coriolis force shapes the convection. The convective flows become organized. Instead of random, chaotic churning, you get large-scale coherent motions ordered by the rotation. And those coherent motions of electrically conducting material are far more efficient at generating a large-scale magnetic field than chaotic random turbulence would be. In this scenario, the seed field that already existed, the magnetic field from the progenitor star, which was itself perhaps already thousands of times stronger than Earth's field, and which gets compressed and concentrated enormously by the collapse just as the rotation does, gets taken up into these organized convective flows and amplified rapidly and violently over the first few seconds. Duncan and Thompson, and then Thompson and Duncan, in a subsequent 1993 paper, worked through the mathematics. The upshot was that in roughly 10 seconds, possibly less, this convective dynamo process could amplify the magnetic field by a factor of perhaps 1,000 or more, reaching the extraordinary surface fields we observe in magnetars. And then, as the neutron star cools and its interior solidifies and the convection dies down, the field is essentially frozen in place. Locked into the star, that is the picture. A millisecond rotation rate, violent convection driven by neutrino-heated boiling, a Coriolis-organized dynamo running for 10 seconds or so, amplifying a seed field by a factor of 1,000 and then stopping, leaving behind a magnetic fossil of that brief, violent process, frozen into a city-sized remnant that will carry it for the next 10,000 years. 10 seconds, that is, in one telling of the story, how the strongest magnet in the universe is made. In 10 seconds, in the immediate aftermath of a stellar death, before the explosion that will tear the star apart has even finished propagating outward. There is something almost breathtaking about that time scale if you sit with it for a moment. The supernova itself will be visible for weeks, the light curve, the expanding shock wave, the nebula, all of that plays out over centuries. But the magnetization, like the thing that makes the difference between an ordinary neutron star and a magnetar, that may be decided in the first 10 seconds of the neutron star's existence, in a window so brief that by the time any electromagnetic signal from it could reach us, it is already over. But here's where it gets interesting, or rather, here's where it gets uncertain. Because Duncan and Thompson's convective dynamo story requires that millisecond spin rate, a very fast initial rotation, and while we know some neutron stars spin fast, we don't know with confidence that magnetar progenitors consistently spin that fast at birth, or why some collapsing cores would spin faster than others. And there is another hypothesis entirely, one that doesn't require the fast spin at all. This is the fossil field theory. The idea is both simpler and in some ways more mysterious. Some stars, it turns out, have unusually strong magnetic fields for ordinary stars. They're called AP stars, a class of chemically peculiar stars with surface fields measurable in thousands of Gauss, which is extraordinary for a main sequence star. If such a magnetically enhanced star undergoes a supernova at the end of its life, the magnetic flux, a quantity related to the total magnetic field threading a given area, is conserved during the collapse. Not amplified by a dynamo, just preserved. But here is the thing about conservation during collapse. The area gets enormously smaller, and so the field strength, which scales with how tightly the flux is concentrated, becomes enormously larger. The numbers work. A progenitor star with an unusually strong field of perhaps 10,000 to 100,000 Gauss, collapsing from a radius of perhaps 100,000 kilometers down to a neutron star radius of 10 kilometers, would see the magnetic field increase by the square of the radius ratio. That ratio is 10,000 to 1. Squared, it's 100 million to 1. Even starting with a modest field, you end up with something extraordinary. In this picture, you don't need a convective dynamo at all. You don't need a millisecond spin. You just need the right progenitor star, one that was already more magnetic than average. The field wasn't generated in the 10 seconds after collapse. It was there all along, buried in the star's history, and the collapse simply concentrated it into a tiny sphere. Now, are both hypotheses right? Is one of them wrong? The honest answer, as of what we currently know, is that the debate is genuinely open. Researchers, including Domitilla De Campli and colleagues, and in a different line, Luca Ferrario and Dayal Wickramasinghe in a 2006 paper, and later reviewed in a 2021 overview by Esposito and collaborators, have explored the fossil field route seriously, and it is not dismissed. It is a live option. Some evidence points one way, some the other. The real answer may well be that both mechanisms operate, perhaps in different magnetars, perhaps in combination within the same magnetar, the dynamo amplifying an already enhanced fossil field rather than starting from a typical weak seed. What is not in doubt is the existence of the extraordinary field. It's there. We measure it. We see its effects. The debate is about which path through stellar evolution and gravitational collapse most reliably produces it. This is the kind of open question that makes astrophysics interesting to work in and interesting to think about as you settle into a quiet night. The universe presents us with the finished product, this extraordinary humming city-sized sphere of magnetized dead star matter. And we are still working backward to understand exactly what series of events in those first frantic seconds produced it. And there is a third piece of the picture, one we touched on before but want to linger on now, the possibility that what we measure on the surface is not the whole story. The field we detect, the one that gives us those surface field strengths of 10 to the 14th to 10 to the 15th Gauss, is what's called the dipole field, the large-scale field that reaches outside the star and that we can measure by watching the star's electromagnetic emissions and tracking how rapidly its rotation slows down. But inside the star there may be a different, stronger structure. The magnetic field inside a neutron star isn't necessarily a simple bar magnet dipole. It can also have a toroidal component, field lines that loop around inside the star rather than extending outward, like coils of wire wrapped around the inside of a sphere. These toroidal fields don't reach out to where we can measure them directly. They are hidden, and theoretical models of magnetothermal evolution in neutron stars, including work by Vigano and collaborators, suggest that in some cases the internal toroidal field may be considerably stronger than the external dipole field we observe. The internal field may be more intense than the surface field. The star we're measuring from across light years might be even more magnetic than the number on the page already suggests. This is humbling. We measure these objects from 50,000 light years away, and we suspect the number we're getting might be the underestimate. Now, you have the field, and you have a rough picture of how it forms. But there is another thing the magnetic field does to a magnetar, something more violent and more immediate than the slow decay we talked about before. Something that generates the bursts we actually observe. Something that transforms a quiet, steadily glowing neutron star into a periodic source of devastating high-energy radiation. This is the starquake. Let's think for a moment about the structure of a neutron star. On the outside, there is a crust, a solid, crystalline layer composed mostly of heavy atomic nuclei arranged in a lattice. Iron and heavier elements packed together under gravity so intense that the whole concept of a normal solid seems barely adequate. This crust is extraordinarily stiff and strong. The atomic nuclei in it are organized by a combination of nuclear forces, electromagnetic forces, and the extraordinary pressure of the neutron-rich fluid beneath. Physicists estimate that the crust of a neutron star may be the strongest material that exists, perhaps 10 billion times stronger than steel in terms of its ability to resist deformation before it fractures. But the magnetic field inside the magnetar is not static. It evolves. Slowly, over years and decades and centuries, the field changes its configuration. Field lines shift, stress builds up in different parts of the interior, and that stress is communicated to the crust. The crust is threaded by magnetic fields, and as those fields evolve, they pull and push on the crystal lattice of the crust. You can think of it loosely like the tectonic plates of the Earth. The Earth's crust is rigid too, in a relative sense, but it sits atop a flowing mantle, and the convective motions beneath put the plates under stress. That stress accumulates over years and decades and centuries, and then it releases, suddenly, discontinuously, in an earthquake. The plates crack or slip, energy stored as elastic stress in the rock is released in seconds, and the ground shakes. A magnetar does something analogous. The evolving magnetic field stresses the crystalline crust. The stress builds, and then at some point the crust can no longer maintain its integrity. It cracks, or more precisely, it suddenly yields. A section of the crust shifts its configuration in a large-scale rearrangement, slipping along a line of weakness like a continental fault, but on a sphere with the density of an atomic nucleus, where even a tiny fractional motion releases an almost incomprehensible amount of energy. This is what Christopher Thompson and Robert Duncan described theoretically in a 1995 paper and what subsequent modeling work, including that of Stuart Lander and collaborators, has explored in more detail. The crust of a magnetar snapping under magnetic stress is a starquake. And a starquake does two things. It releases a burst of energy in the form of high-energy photons, X-rays and gamma rays, in a flash that can be detected from across the galaxy. And it can also rearrange the external magnetic field configuration, disturbing the magnetosphere of the star, the region just outside it where the field lines extend into space in ways that can produce even more energetic events. Most magnetar bursts, the routine ones, the smaller ones that happen periodically, and have been catalogued in the years since we started watching these objects carefully, are probably crust-cracking events on modest scales, a section of crust a few hundred meters across, shifting by a fraction of a millimeter. By human standards, that sounds trivial. By the standards of a neutron star crust, it's an earthquake felt across the whole star, and the energy release can be 1,000 times more powerful than anything Earth's geology can manage. And then there are the giant flares. The giant flares are something else entirely. They are not just big starquakes. December 27, 2004, SGR 1806-20, that was a giant flare. In that event, the physics shifted from a crust-cracking picture to something more sweeping, a large-scale instability involving not just the crust, but the magnetosphere, the external field, the whole electromagnetic environment of the star reorganizing itself in a catastrophic cascade. In a giant flare, the initial spike, that burst in roughly 1/5 of a second that outshone the sun's entire output for 250,000 years, is followed by a pulsating tail of emission that lasts for minutes. The pulsation period matches the rotation of the star, radiation trapped by the magnetic field, circling the star as it rotates. The field reorganizes, the star settles, and for several minutes the residual energy rings like a bell struck very hard, fading away as the magnetosphere finds a new, lower energy configuration. Thompson and Duncan's 1995 theoretical work on starquakes and the external field instability predicted something like this, though the events were poorly understood from the observational side until the 1979 flare, which we'll come back to, and then the 2004 one gave the field detailed data to work with. Lander and colleagues, in more recent work from 2015, refined the picture of how the crust yields and how the magnetic energy stored in the external field gets released. The picture is not simple. There are several possible mechanisms for how a giant flare initiates, and discriminating between them observationally is still an active area of work. But the broad outline is settled: a large-scale magnetic instability in the crust, or magnetosphere, a sudden energy release, a brief dawn of X-ray and gamma-ray light so intense it crosses a galaxy and still has enough energy to reach down into the upper atmosphere of a planet orbiting an unremarkable star in one of the spiral arms. That planet being, of course, ours. And here is a question worth turning over for a moment, because we've spent some time now understanding the starquake, the crust, the stress, the crack, the energy release. But where does the stress come from in the end? It comes from the evolving magnetic field. And the evolving magnetic field evolves because it is slowly decaying, and the decay of the field is the process that powers the whole star. Which means every burst a magnetar emits is, in a very real sense, the star spending down its magnetic inheritance. Each flare, each burst, each starquake, a little more of the frozen-in energy from those first 10 seconds after collapse, releasing itself back into the cosmos. A magnetar is a star living off its savings, very slowly, irreversibly, spending the magnetic wealth accumulated in the moments of its birth. And as it spends, the field weakens, the crust settles, the bursts become less frequent, less energetic. Over roughly 10,000 years of active life, and we have confirmed only about 30 active magnetars in the whole galaxy, partly because this active phase is so brief, The magnetar fades. The field weakens below the threshold needed to power those extraordinary bursts. The object becomes a quieter neutron star. The galaxy's population of neutron stars likely contains many millions of these objects, once active magnetars now dormant, carrying weaker fields, spinning slowly, cooling gradually, nearly indistinguishable from the enormous graveyard of ordinary neutron stars that litter the Milky Way. The active magnetar is a brief, violent, luminous phase in what will be a very long afterlife. And then there is the mystery of the Westerlund 1 magnetar. This is the story we promised to tell, the one that tugs at the neat picture and asks whether stellar evolution is ever quite as straightforward as we'd like. Westerlund 1 is a massive star cluster, one of the most massive in the entire Milky Way. It sits roughly 15,000 light-years away from us. The cluster contains an extraordinary collection of massive stars in various stages of their lives. Wolf-Rayet stars, luminous blue variables, red supergiants. It is in many ways an exceptional place, a kind of stellar wildlife reserve for the biggest, most profligate stars the galaxy has made. And at its center, there is a magnetar, CXOU EG16471 2455216, a confirmed magnetar sitting inside this cluster of giant stars. Now, the problem, or more precisely, the puzzle. When you look at the stars in Westerlund 1 and estimate the minimum mass a star would have needed to have already evolved off the main sequence and exploded as a supernova, to have produced the magnetar we see, the number you get is somewhere around 40 solar masses. Possibly more. And here is why that's strange. A star of 40 solar masses or above is, in standard stellar evolution models, expected to produce a black hole when it dies, not a neutron star. The mass is too great. The core it leaves behind should, in theory, exceed the maximum mass a neutron star can support and collapse all the way. It shouldn't leave behind a city-sized remnant at all. It should disappear behind an event horizon. And yet there it is. A magnetar. A neutron star. Sitting in a cluster of stars that tells us the progenitor was probably far too massive to produce it by conventional stellar evolution expectations. This paradox was explored in work by Michael Muno and collaborators in 2006, and by Clark and collaborators working on the Westerlund 1 system. One of the leading explanations involves a binary companion. If the progenitor star had a close binary companion, that companion could have stripped a substantial fraction of the progenitor's mass during the red supergiant or Wolf-Rayet phase of its evolution. Essentially, the progenitor lost mass to its neighbor before it died. This is called mass transfer, and it is common in close binary systems. The star that ends up exploding is therefore significantly less massive than its original birth mass, and it leaves behind a neutron star rather than a black hole. But this explanation comes with its own implications. If mass transfer shaped the outcome in Westerlund 1, then the formation of a magnetar, as opposed to an ordinary neutron star, might sometimes depend not on the isolated physics of the collapse, but on the previous history of mass exchange between two stars. The magnetar formation channel might be broader and stranger than a simple story of collapse and dynamo would suggest. The initial rotation rate of the collapsing core might be influenced by the history of the binary interaction. The mass stripped by the companion, the angular momentum exchanged, the timing of the explosion, all of these could in principle affect whether the remnant ends up as a magnetar or something else. This makes the Westerlund 1 magnetar not just a puzzle about a specific object, but a hint that the full magnetar formation story may be more tangled with stellar history, with the complicated social lives of stars in pairs and clusters, than a clean single-star model would imply. Stellar evolution is rarely as isolated as our textbook diagrams suggest. Stars are born mostly in clusters. Many of them are in binary or multiple systems, and the interaction between partners over millions of years of coevolution can profoundly reshape what each star becomes. So when we ask how a dead star ends up this magnetized, we might sometimes need to answer, partly because of what another star did to it, partly because of a companion now gone or now orbiting in the background, invisible and unhelpful, having already done its work. The magnetar sits there, in Westerlund 1, spinning quietly, its starquake clock ticking, embedded in this extraordinary cluster of massive stars, and it remembers in its field and in its spin what it was, and what happened to it, and who, perhaps, it was paired with. We read those memories poorly, from across 15,000 light-years, with instruments that can only catch the photons the object is willing to send us. You can feel, maybe, why people who work on magnetars find them endlessly compelling. They are, in one sense, very simple. A ball of neutrons, a massive field, a slow spin, a periodic burst. In another sense, they open onto nearly every interesting frontier in contemporary astrophysics. The behavior of matter at nuclear density, the limits of quantum electrodynamics, the statistics of stellar evolution, the physics of magnetic field generation, the origin of the most energetic radio bursts in the universe. Pull on any one thread and you find yourself somewhere unexpected. And speaking of unexpected, the origin mystery doesn't end with the dynamo or the fossil field or the progenitor paradox. There is still the question of the hidden interior, which we will let sit for now as we move forward. Still the question of where the truly extraordinary cases, SGR 180620 with its field at the highest end of the confirmed magnetar distribution, 10 to the 15th Gauss, sit within the distribution of formation histories. Why are some magnetars more extreme than others? Is it simply a matter of initial spin rate, the strength of the progenitor's seed field, the details of the binary interaction, some combination that we haven't yet found the right way to weight? These are genuine research questions, not rhetoric, not filler to stretch a pleasant night of listening. Real open questions that are being worked on by real people right now, writing papers, building models, waiting for the next burst from some known magnetar or the discovery of a new one that might provide the data needed to make a little more progress. There is something I find quite peaceful about that. About the idea that somewhere, in an office or at a kitchen table, or hunched over a laptop in the middle of the night, someone is turning over the formation history of Westerlund 1's magnetar, or modeling the toroidal field configuration inside SGR 180620, or running magnetothermal evolution simulations to see which initial conditions produce the observed distribution of active magnetar lifetimes. The universe poses the questions, we work on them carefully over years, and the answers, when they come, are always a little more interesting than the questions suggested they would be. This is, in the end, what the magnetar is doing for us. It is not just a spectacular natural phenomenon to photograph and catalogue and describe in superlatives. It is a laboratory. It is an object whose extreme conditions, impossible to replicate in any human-made device, inconceivable in any ordinary terrestrial setting, allow us to test and probe and sometimes surprise our best physical theories. The laws of quantum mechanics, the behavior of dense matter, the way magnetic fields evolve in environments utterly unlike anything else we know about. The magnetar is nature doing an experiment that we couldn't design, and then publishing the results in X-rays and gamma rays and the occasional radio burst for those patient and clever enough to read them. The crust cracking, the field freezing in, the dynamo running for 10 seconds and then stopping, the fossil field concentrating under gravity, the toroidal field hiding inside, the progenitor being stripped by its companion, all of it written into this 20-kilometer sphere, spinning slowly now, 2 or 12 seconds per rotation, gradually fading, spending down its magnetic inheritance year by year and burst by burst. The strongest magnet in the universe is also one of the most patient puzzles in it, and we are still carefully working out how to read it. Let us settle then into the strangest part of the magnetar story, because everything we have covered so far, the collapse, the dynamo, the frozen field, the starquakes, the energy budgets, all of that has been physics operating in registers we at least recognize, extreme registers. Registers that stretch ordinary intuition far past its comfortable range, but registers where the rules of physics are still, fundamentally, the ones we know from our labs and our textbooks. What comes next is something else. When a magnetar's field climbs past a certain threshold, a threshold that has a precise name and a precise number, the physics stops being merely extreme and starts being genuinely different. The vacuum itself changes, empty space, the nothing between objects, the absence of everything, stops behaving the way empty space is supposed to behave. And that is one of the quietest, strangest, most beautiful things that any object in the universe is known to do. The threshold is called the quantum critical field. Sometimes it goes by another name, the Schwinger limit, after the physicist Julian Schwinger, who worked out some of the relevant mathematics. The number is approximately 4.4 times 10 to the power of 13 gauss, written out 44 trillion gauss. It sounds enormous, and it is. It is a field roughly 1 billion times stronger than the strongest sustained magnet ever built in a human laboratory. And yet a typical magnetar sits comfortably above it. A strong magnetar has a surface field 10 to 20 times higher than the Schwinger limit. Some sit 100 times above it. So what happens at the Schwinger limit? What changes? To understand it, you need a small piece of background. In the version of physics we call quantum electrodynamics, the theory that describes how light and matter interact at the deepest level we currently understand, the vacuum is not quite nothing. It is not the absolute emptiness of classical imagination, the perfect inert void between objects. It is instead a seething background of what physicists call virtual particles, pairs of electrons and their antimatter partners, positrons, flickering into brief existence and then annihilating again, constantly, everywhere, too fleeting for us to catch directly, but real enough to affect measurements in subtle ways. In ordinary conditions, conditions you would encounter anywhere in the observable universe except the immediate vicinity of a magnetar, this quantum background has no preferred direction. It is the same in all directions. A photon, a particle of light, passing through a vacuum moves in a straight line, and its properties are not affected by the vacuum itself. The vacuum is isotropic, neutral, a featureless through space for light to travel in. A magnetic field changes that. A strong enough magnetic field imposes a direction on the vacuum because magnetic fields are directional. They have a north and a south, lines of force running from one to the other. When the field is strong enough, those virtual particle pairs are no longer isotropically random. They are oriented. They align with the field lines. And aligned virtual particles affect light differently depending on whether that light's electric field oscillates along the magnetic field lines or across them. Light coming in parallel with the field behaves one way. Light coming in perpendicular behaves differently. The speed of light, which is actually not quite the same for both orientations in a strong enough magnetic field, differs for the two. This means that the vacuum, in the presence of an intense magnetic field, becomes birefringent. Birefringence, you may have encountered it in a different context. Certain crystals, calcite is the classic example, split a beam of light into two beams because they have an internal structure that treats different polarizations differently. The crystal is optically anisotropic. Light sees it differently in different directions. If you place a calcite crystal over text on a page, you see a double image. The crystal structure is doing to light what the magnetar's field does to the vacuum itself. The magnetar makes the empty space around it behave like a crystal. This is not metaphor. This is a prediction of quantum electrodynamics that has been sitting in the equations since the middle of the 20th century, waiting for an environment strong enough to display it. The prediction is that in a sufficiently intense magnetic field, one approaching or exceeding the Schwinger limit, the vacuum becomes birefringent. Light polarized in one direction travels at a slightly different effective speed than light polarized in the perpendicular direction. The difference is tiny in ordinary magnetic fields, but near a magnetar the field is strong enough that the effect should be, in principle, observable. And in 2016, a team led by Roberto Mignani reported evidence that it had been observed, not at a magnetar, but at a different neutron star, one called RxJ1856.5-3754, a relatively nearby isolated neutron star sitting a few hundred light-years away. The team used the Very Large Telescope in Chile to measure the polarization of the optical light coming from this star. What they found was a degree of linear polarization that was substantially higher than what would be expected from ordinary astrophysical sources. The data were consistent with the vacuum birefringence predicted by quantum electrodynamics in the neutron star's powerful magnetic field. Not proven beyond all doubt, not a clean laboratory result, but observationally supported in a way that had not been demonstrated before. Empty space twisted by a magnetic field, showing its structure in the polarization of starlight. This matters for reasons that go well beyond the specific curiosity of magnetars. Quantum electrodynamics is the most precisely tested physical theory in human history. Some of its predictions have been confirmed to better than 1 part in 10 billion, and yet one of its fundamental predictions, that intense magnetic fields restructure the vacuum, had never been directly confirmed in any setting. The magnetar and its somewhat quieter cousin, RxJ1856.5-3754, are the only places in the universe where the fields are anywhere near strong enough to show this effect. They are natural QED laboratories that no particle accelerator, no cryogenic magnet, no human engineering project can replicate or approach. In this way, the magnetar is not just the strongest magnet in the universe, it is the only test bench in existence for a particular corner of our deepest physics. And it is out there, spinning slowly, spending down its field, not caring about any of this, while we point our telescopes at it and try to read what it is telling us. But the birefringence is not the only QED effect the magnetar's field produces. The field also does something to ordinary matter, to atoms themselves, that has a quality almost of the surreal. In ordinary conditions, an atom is essentially spherical. The electron cloud surrounding the nucleus is spread in 3 dimensions, occupying a fuzzy quantum sphere. The shape varies slightly depending on which orbital the electrons occupy, but the rough picture is one of a compact, roughly spherical region of electron probability surrounding a tiny nucleus. Near a magnetar, in a field approaching or exceeding the quantum critical threshold, this picture changes completely. The magnetic force on the electrons becomes so dominant, so far exceeding the electrostatic force that ordinarily dictates the atom's shape, that the electron cloud collapses anisotropically. It is squashed, flattened, elongated. Specifically, the electron cloud is compressed perpendicular to the magnetic field lines and stretched along them, turning the spherical atom into something that looks more like a long, thin cylinder, a needle-shaped object aligned with the field direction. Not every atom near the magnetar, not atoms far away, but at the surface in the intense field, the atoms are not round anymore, they are cylinders. Polymer chain-like structures form, threading along the field lines. The entire chemistry of matter, which is at its foundation, the behavior of electron clouds and how they interact with other electron clouds, is rewritten. Biological molecules with their subtle geometries and their precisely shaped binding sites would not exist in recognizable form in that environment. The shape of a molecule is part of what makes it a molecule, Reshape the atoms and you change the chemistry. Change the chemistry and you dissolve the biochemistry. This is why physicists say that approaching a magnetar closely would deform the atoms of your body, not poetically, not as a colorful way of saying it would hurt, but literally. The electron clouds defining your atoms would be reshaped by the field, and the molecules, depending on those shapes for their function, would cease to function. This is distinct from being crushed by gravity, distinct from being burned by radiation, distinct from being shredded by tidal forces. It is death by magnetism at the quantum level, and it would begin at roughly 1,000 kilometers from the surface. The magnetar does physics that we cannot do anywhere else, and it does it continuously in the quiet between bursts, sitting there in the X-ray sky, squeezing its atoms and rewriting its vacuum and spending its field one slow rotation at a time. Let's open another thread, because the magnetar turned out to have one more surprise waiting, and this one arrived in April 2020, and it connected a very old mystery to a very powerful object in a way that changed the field of radio astronomy. For several years before 2020, radio astronomers had been puzzling over a phenomenon called fast radio bursts. The name is straightforward. They are bursts. They are fast. They are radio waves. A fast radio burst lasts perhaps a millisecond. In that millisecond, it emits as much radio energy as the sun emits across all wavelengths in 3 days. They come from enormous distances, cosmological distances in most cases, from galaxies hundreds of millions or billions of light years away. They arrive with no warning, they vanish, and most of them are not repeated, making follow-up observations nearly impossible. The mystery was simple and total. Nobody knew what made them. Dozens of explanations were proposed: merging neutron stars, evaporating black holes, alien civilizations, exotic phase transitions in the early universe. The honest answer, for years, was that fast radio bursts were one of the cleanest unsolved problems in astrophysics: real, measured, repeatable as a phenomenon, and completely unaccounted for. Then, on April 28, 2020, something happened. A magnetar in our own galaxy, SGR 1935 Plo 2154, sitting somewhere between 30,000 and 50,000 light-years away in the general direction of the constellation Vulpecula, fired a burst. This was not remarkable on its own. SGR 1935 Plo 2154 is an active magnetar and it fires bursts regularly. What was remarkable was the radio component of this particular burst, because along with the X-ray and gamma-ray emission typical of a magnetar outburst, this burst produced a bright, brief, energetic radio flash, a fast radio burst. 2 separate instruments detected it. The Chime Radio Telescope in British Columbia, a remarkable stationary array designed to survey large swaths of sky simultaneously, caught it, and STARE-2, a small network of radio antennas designed specifically to watch for FRBs within or near the Milky Way, also caught it. The event was designated FRB 2004-28 after the date it arrived. This was the first time a fast radio burst had been traced to a known source within our own galaxy, and that source was a magnetar. The implications were immediate. If a galactic magnetar could produce a burst this bright, then magnetars were almost certainly responsible for at least some of the extragalactic fast radio bursts being detected from enormous distances. The extreme field strength, the starquake mechanism, the sudden restructuring of the magnetosphere during an outburst, these provided a physically plausible engine for the radio emission. The mystery was not fully solved. Some FRBs, particularly the repeating ones with peculiar characteristics, may involve other mechanisms or environments. But a major piece of the answer had just been locked in. SGR 1935 Plo 2154, an active galactic magnetar, had connected 2 separate fields of observation and resolved one of the most prominent open questions in radio astronomy: in the space of a single millisecond burst. The strongest magnet in the universe is also, it turns out, a radio transmitter. Not efficiently, not intentionally, but powerfully and in a way that announces its presence across tens of thousands of light years. This brings us to something worth doing slowly. We have been moving forward through the physics of magnetars, what they are, how they get their fields, what those fields do to matter and space and light, what they connect to in the wider universe of phenomena. But there is a thread we should follow backward as well, because the magnetar did not arrive in our understanding with an explanation already attached. It arrived as a mystery, and the mystery is, in its own way, as interesting as the answer. March 5th, 1979. 9 spacecraft are scattered across the inner solar system, each on its own trajectory, carrying its own instruments, conducting its own observations. They include probes of various design and purpose, the kinds of missions that are launched with one goal in mind and then, because space is space, encounter the unexpected. At 10:50 Universal Time on that morning, something hits them, not physically, but every gamma-ray detector, every X-ray instrument on every one of those 9 spacecraft registers an abrupt, overwhelming spike of high-energy radiation. The detectors saturate, they hit their maximum measurable value and pin there, the way a voltmeter pins when you connect it to something outside its range. The instruments are not broken. The signal is simply larger than the scale the instruments were designed to handle. The burst lasts seconds, then it modulates, pulsing with a period of about 8 seconds for several minutes. And then it fades. It is the brightest event any of those instruments had ever recorded. And because the 9 spacecraft are at different positions in the solar system, each one receives the signal at a slightly different time. The timing differences are small, fractions of a second in some cases, but they are measurable. And from those timing differences, astronomers can triangulate. They can calculate the direction the signal came from. When they do, the direction points to a region of the sky in the constellation Dorado. More precisely, to a region coinciding with a supernova remnant called N49, which sits in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, roughly 160,000 light-years away. The object that sent this signal was eventually designated SGR 0526-66. This was a discovery, though it took years to understand what had been discovered. The object was placed in a new category, soft gamma repeaters, objects that produced repeating bursts of somewhat softer gamma rays. But the physical explanation was absent. Nobody knew what these things were. The tools to understand them, the field equations, the theoretical framework, the connection to neutron star physics, did not yet exist in assembled form. It took 13 years. In 1992, Robert Duncan and Christopher Thompson published a theoretical paper that proposed a new class of neutron star, an object with a surface magnetic field orders of magnitude stronger than any previously imagined, powered not by its spin, but by the slow decay of that extraordinary field. Duncan and Thompson showed that such an object could be formed if a newborn neutron star was spinning fast enough and convecting violently enough in the first seconds after collapse. They showed how the dynamo would run, they computed the field strengths, they predicted the X-ray luminosities, and they gave the object a name, magnetar. The word was coined in 1992, 13 years after the observation that first demanded an explanation. The March 5th, 1979 event, that initial, saturating, overwhelming burst from a galaxy 160,000 light-years away, was the first giant flare in the historical record, the discovery event, the thing that opened the field. And for more than a decade, it sat there in the literature, classified, catalogued, genuinely mysterious, waiting for Duncan and Thompson to work out what it was. Science often works this way. The observation comes first. The framework follows, sometimes much later. sometimes built by someone who was not yet a scientist when the observation was made. The universe does not wait for the theory before producing the phenomenon. Now let us count what we have. As of the most recent version of the McGill Magnetar catalogue, roughly 30 confirmed magnetars are known. 30 in a galaxy containing something on the order of 2 to 400 billion stars. In a galaxy that has been forming stars and ending them in supernovae for 10 billion years or more. 30. The number seems impossibly small, and in one sense it is, because it reflects not the true number of magnetars in the galaxy, but the number we can currently detect in their active phase. A magnetar is only visible as a magnetar for a limited window of time, roughly 10,000 years of intense activity, during which the field is strong enough to power bursts and the luminosity is high enough for our instruments to register it at galactic distances. After that, the field decays. The magnetar quiets. Its X-ray luminosity drops. Its bursts stop. It becomes, from our observational perspective, just another neutron star, or perhaps too dim to identify as any particular kind of neutron star. The galaxy has been making massive stars and ending them in supernovae for billions of years. A fraction of those collapses, the ones with the right initial conditions to run the dynamo or the right magnetic heritage to concentrate a fossil field, produce magnetars. If even a small percentage of the hundreds of millions of neutron stars estimated to exist in the Milky Way were born as magnetars, then the number of dormant, spent, faded magnetars out there is not 30. It is millions.
Millions of dead, cooling objects that were once the most magnetically violent things in the galaxy, now sitting in darkness, their fields gradually relaxing toward ordinary neutron star values, invisible to us unless something disturbs them. There is a population of ancient, quieted magnetars scattered through the galaxy, and we pass through their distances without any instrument pointing at them, without any signal reaching us, without knowing they are there.
This is one of the persistent challenges of magnetar astronomy. We sample only the active phase, we see only the bursts. The true census of how many magnetars the galaxy has produced, what their field strength distribution looks like, how common the conditions for magnetar birth really are. All of that requires inferring the invisible majority from the visible minority. And that inferring is hard. The magnetothermal evolution models built by researchers including Diego Vigano and collaborators in work published around 2013 attempt to follow a magnetar's magnetic field and temperature simultaneously through its lifetime. The field decays, heating the crust as it does so, which affects the X-ray emission, which is what we observe, which then constrains the models. The models are sophisticated. They are also constrained by a very small number of known objects and a relatively short baseline of detailed observation. What they tell us is broadly consistent with the picture of magnetar decay and eventual dormancy, but the precise rates, the precise timescales, the precise conditions that separate a magnetar-forming collapse from an ordinary neutron star-forming one, these remain areas of active work. The question underneath all of this, the one the field is working toward, is this: what fraction of neutron star births are magnetar births? Is it rare or common? Is it 1 in 100 or 1 in 10 or 1 in 1,000? The answer matters for understanding how much magnetic energy the galaxy has deposited into its neutron star population over its lifetime. It matters for understanding what triggers the most energetic events in the local universe. And it matters for understanding fast radio bursts, because if magnetars make FRBs and FRBs are detectable from cosmological distances, then the magnetar birth rate is connected to the FRB rate is connected to the star formation history of the universe across billions of years. A small object, 20 kilometers wide, connects to the largest scales of cosmic time. And this feels like the right place to open this window, because you may have been holding a small worry at the back of your mind, a worry that has been politely waiting while we talked about ionospheres and decaying fields and distant galaxies. Let us close the loop that the opening of this journey left open. The 2004 flare from SGR 1806-20 reached Earth and disturbed the ionosphere. That is real and verified. The March 5, 1979 event from SGR 0526-60 swept 9 spacecraft across the solar system. Real. The field of an active magnetar, were you to be close enough, would deform the atoms of your body at roughly 1,000 kilometers. Real. The credit card erasure at roughly halfway to the moon. Real in its order of magnitude illustration. How close would a magnetar actually have to be to threaten life on Earth in a more serious way? The answer, drawn from the energetics of the observed flares and the modeling of atmospheric effects, is this. A magnetar would need to be within roughly 10 to 15 light-years of Earth to pose a genuine threat to the biosphere from a giant flare. At that distance, the gamma and X-ray radiation from an event like the December 27, 2004 burst would be intense enough at Earth's surface to cause meaningful damage to the ozone layer, with downstream effects on life that could be severe. 50,000 light-years away as SGR 1806-20 is, the flare is energetic enough to disturb the upper atmosphere, but causes no ground-level harm. The atmosphere absorbs the high-energy photons before they reach us. We were bathed in the ionosphere-disturbing pulse on December 27, 2004, and none of us felt it or knew about it as it happened. The nearest known magnetar is thousands of light-years away, not tens, not hundreds, thousands. No confirmed magnetar sits within 10 to 15 light-years of Earth. No confirmed magnetar sits within hundreds of light-years of Earth. The space immediately around us, the small, quiet neighborhood of the galaxy we happen to occupy, contains no active magnetar, and if there are dormant, extinct magnetars nearby, their fields have decayed to the point where they no longer produce bursts, no longer emit anomalous X-rays, no longer constitute any hazard whatsoever. A dead magnetar that has spent down its field over millions of years is simply a neutron star. Remarkable for what it once was, no longer remarkable for what it does. We are safe. The universe is violent. It contains objects whose energy release in fractions of a second surpasses the sun's output across geological ages, and we sit at a comfortable remove from all of them, separated by the generous distances of interstellar space, protected by the vast emptiness between stars. The 2004 event was real. The ionospheric disturbance was real. The science is precise and the effect was measured, and it left nothing on the ground except data for instruments designed to watch for exactly that kind of signal. That is the honest reassurance, not, don't worry, it's fine, but the numbers have been run, the distances are known, the nearest is nowhere near close enough, and the atmosphere absorbed the most energetic event of its kind that instruments have ever recorded from an extragalactic direction. You can let that worry go. Whatever else the night holds, this particular kind of cosmic violence is not pointed at us. And even when it was, from 50,000 light-years away, in December of 2004, the worst it managed was a small perturbation in the ionosphere, measured by radio antennas invisible to every person alive. So let us come to rest here, on the far edge of what we know about these objects, and let us look at the whole shape of it, all at once, before we sleep. A star more massive than you can quite hold in your mind, 10, 20, 30, 40 times the mass of our Sun, burns for millions of years, converting hydrogen to helium, helium to carbon, carbon to oxygen, all the way up to iron. Iron is the end of the chain, the bottom of the nuclear energy ladder. The star's core, in the last moments, is trying to maintain itself against gravity with no fuel left to burn. it fails. The core collapses in under a second, falling inward faster than sound, faster than ordinary matter can respond. And then the infalling material meets the stiffness of nuclear matter and bounces, and the shockwave propagating outward tears the outer star apart in a supernova. What is left at the center is a ball of neutrons, 20 kilometers across, more than a solar mass. Spinning, in the case of a magnetar, unimaginably fast, a full rotation in something close to a millisecond, 1,000 rotations per second in those first chaotic moments.
And it is hot. Unimaginably, violently, extraordinarily hot. So hot that the interior is convecting. Enormous columns of superhot material rising, cooler material sinking, the whole interior churning like a boiling pot at temperatures that make the surface of the sun seem lukewarm. And in that churning, in that convection, in the presence of rapid rotation, something runs. A dynamo.
The same basic physics that runs in Earth's liquid iron core, maintaining our planet's modest magnetic field, runs here, but in conditions so extreme, at rotation rates so high, with convective violence so intense, that what comes out is not a field of half a gauss. What comes out is a field of a quadrillion gauss, or close to it. The convective dynamo amplifies the seed magnetic field, whatever small field the collapsing star brought with it, by a factor that can be 1,000 or more in the first 10 seconds after collapse, and then it stops. The star cools, the convection settles, the field freezes in. What is frozen in is the strongest magnetic field in the universe. Or perhaps, and this is the honest qualification that matters, what is frozen in is a concentrated version of the magnetic field the progenitor star already had. The fossil field hypothesis says the dynamo is not the whole story, or perhaps not the story at all. It says that some massive stars are simply born more magnetized than others, and that when they collapse, the magnetic flux is conserved and concentrated by the compression in the same way that an ice skater pulling their arms in spins faster. The collapse is so extreme, the radius shrinking from something hundreds of thousands of kilometers across to 20 kilometers, that any magnetic field present in the original star is concentrated by factors that can easily reach the values we observe. Which is right, the dynamo, the fossil field, or some combination of the two? The honest answer, sitting here in the middle of the 2020s with everything the field has learned, is that we do not fully know. Both mechanisms are physically plausible. Both are supported by arguments and observations. Neither has been definitively ruled out. The true origin of the Magnetars field is one of the genuinely open questions in astrophysics, a question being worked on with observations from the McGill Magnetar catalogue and with magnetothermal evolution models and with population statistics and with the progenitor associations like Westerlund 1. The universe is, in this respect, keeping some of its cards. The strongest magnet it has made is also one of its more interesting puzzles. And then there is the aftermath. The field does not sit still. It is not a static property. The magnetic field of a magnetar is dynamic, evolving, pushing on the crust from inside, stressing the crystalline neutron-rich lattice of that thin, solid shell, warping the geometry of the magnetosphere above the surface. When the stress exceeds what the crust can bear, when the magnetic pressure accumulated in the interior, in the toroidal field loops that may be even stronger than the surface field we measure, finally overcomes the material strength of neutron star crust. Something snaps, a starquake, a crack propagating across the surface of this 20-kilometer sphere, releasing in seconds the accumulated stress of years. The crust shifts. The magnetosphere reconfigures. The sudden change in field geometry launches an electromagnetic wave of extraordinary intensity outward into space. That wave is the burst. That wave, in the case of December 27, 2004, carried more energy in a fifth of a second then the Sun will radiate across 250,000 years, and it traveled 50,000 light-years and still managed to ionize the upper atmosphere of a planet with a gaseous envelope much thicker and more protective than the interplanetary medium. That wave, in the case of April 28, 2020, was detected as a fast radio burst from a source 30,000 or more light-years away, and it connected the magnetar to one of the most active unsolved problems in modern radio astronomy. That wave, in the case of March 5, 1979, swept 9 spacecraft and opened a field of study that took 13 years to name. The magnetar does not announce itself. It does not schedule its bursts. It sits there in the X-ray sky, fading slowly, pulsing on its slow rotation period. 2 seconds, 8 seconds, 12 seconds. And then, when the internal geometry demands it, it speaks, loudly, briefly, across distances that should make any individual event insignificant and somehow don't. We point instruments at it, we measure the pulse timing, and watch for glitches in the rotation that might signal internal rearrangements. We measure the spectral shape of the persistent X-ray emission and try to infer the field geometry from it. We search for the polarization signal that vacuum birefringence should produce. We count the known magnetars against the population models and try to infer the thousands or millions of dormant ones we cannot see. We build the magnetothermal evolution codes that attempt to follow one of these objects through its entire life, from the hot, spinning chaos of the first seconds after collapse to the quiet, cooling neutron star it eventually becomes. And sometimes the sky gives us a gift, a new burst from a known magnetar, a previously quiescent source coming back to life, a radio burst from a galactic object that was not supposed to emit in radio at all, and we rearrange our observing schedules. We point the X-ray satellites, we open the radio dishes, we collect the data, and we add one more piece to the picture. Think about what this object actually is, from the outside, from the comfortable distance of thousands of light years, from the safe remove of your bed, from wherever in the world you are right now. A ball smaller than your city, smaller than many cities. 20 kilometers is the distance from the center of a moderately sized town to its outskirts. This is not a vast object. It is tiny on any scale that involves stars or planets or even large mountains, and it contains more than the mass of the Sun. Its surface gravity is so intense that a marshmallow falling from a meter above the surface would strike with the energy of a nuclear weapon. A cubic centimeter of its material weighs more than 1 billion tons, and wrapped around it, saturating every cubic meter near its surface, extending outward through space in the geometry of a magnetic dipole, plus all the complex toroidal structure hidden inside, is a field so intense that the empty vacuum around it is no longer optically neutral. Light passing near it is polarized by the vacuum itself. Atoms near its surface are not spherical. They are needles. Molecules as we know them do not exist in its immediate vicinity. The chemistry of matter has been overwritten by magnetism. All of that is packed into something the size of a city, spinning, slowly, radiating, waiting. There are roughly 30 of these we know about. There are, in all probability, millions of their extinct ancestors scattered through the galaxy we live in, invisible, cooling, spent. One of the ones we know about fired a burst in December of 2004 that reached Earth and left a measurable mark on the ionosphere. One of them fired a burst in April of 2020 and solved part of one of radio astronomy's most prominent mysteries. And one of the bursts in 1979 opened the entire field, sweeping 9 spacecraft and confounding astronomers for 13 years before Duncan and Thompson handed the phenomenon a name and a mechanism. You are lying somewhere in the dark, or perhaps drifting through the soft edge of sleep, and the universe is full of these. Full of objects doing physics we cannot replicate. Full of objects holding open questions we are still carefully assembling the tools to answer. Full of objects whose fields have reshaped their local vacuum whose crusts have cracked under magnetic pressure, whose bursts have crossed half the galaxy and still arrived energetic enough to perturb the upper air of a living planet.
And you are part of this same universe. The atoms of your body and the carbon, the oxygen, the hydrogen, the iron in your blood were forged in stellar interiors and dispersed in stellar deaths, not necessarily magnetar deaths, not necessarily the deaths of the most extreme massive stars, but in the full family of stellar processes that the universe uses to build and rebuild its chemistry across time.
The magnetic fields threading through your body are a billion times weaker than the field of SGR 1806-20, but they are fields. They are the same kind of thing, differing only in degree. Your neurons use electrical and magnetic signals. Your blood contains iron. The physics is continuous, from the largest field in the universe to the electrochemical gradients in the cells you are built from. You are not separate from the universe that contains magnetars. You are made of processes that are continuous with the processes that make magnetars, the collapse and the convection and the frozen field, and the crackling crust and the burst traveling 50,000 light years. These are all the universe doing what it does, in the register that particular corner of it permits. Your register is different, quieter, more delicate, but the same underlying physics runs through all of it, from the Schwinger limit to the synapse, from the ionosphere to the heart. That is a good thing to carry into sleep, not frightening, not overwhelming, just quietly true. The same universe that makes the strongest magnet in existence, that freezes a quadrillion Gauss field into a ball of dead star 20 kilometers wide and then lets it snap loose in bursts that cross the galaxy, that same universe makes the particular kind of matter that can lie still in a bed and think about all of this and find it wondrous. We started tonight somewhere else. You were somewhere, in your bed, on a couch, on a train, with a lamp still on or the dark already complete around you. And I asked where in the world you were listening from. I still want to know, because wherever you are, the night sky above you holds the light of the Milky Way, whether you can see it through the clouds and the city glow or not. And somewhere in that band of stars, many thousands of light years away, there are objects spinning slowly in the X-ray dark, their fields decaying year by year, their crusts under quiet stress, waiting for the moment when the geometry demands that they speak again. You will not feel it when they do. The atmosphere will absorb it, the distance will dilute it, but the instruments will catch it and the data will accumulate and the models will be updated and the picture will sharpen a little more. The strongest magnet in the universe is a dead star, a collapsed core, a frozen dynamo, a city-sized impossibility, doing physics the rest of the universe rarely permits. We have known about it for barely 50 years. We have had a name for it for barely 30. And we are still, with patience and curiosity and the slow accumulation of nights' worth of careful observation, working out all the things it is trying to tell us. If you enjoyed this slow journey through some of the stranger corners of astrophysics, a gentle like or subscribe means a great deal. Small creators like this channel genuinely rely on your support to keep making these nights possible. And do tell me in the comments, where are you listening from tonight, and what time is it in your corner of the world? I read them. Every one. Until next time, take the wonder with you. Calm mind, clever dreams. I'll be here tomorrow night.